In the previous video, we've had a look at the magnetic field due to a solenoid. Now, a solenoid is a simple coil of wire that is straight. Now, if we take a solenoid and join both the ends of a solenoid to each other to form a ring kind of a thing, so it's a kind of a coiled ring. So if we form that shape, that would be called a toroid. And that is the spelling of it. And if I just draw it quickly, so we have a coil that is in the shape of a ring, just like that. Yeah, sort of like that. So it's a solenoid, but in the shape of a ring, right? And in some way you can just put a small battery here in some point. I'll just not draw it for now, but yeah, you have some current in the toroid now. It seems so if we analyze the magnetic field of a toroid, there would be some magnetic field inside the toroid, but you can obviously see that it would go, and as it goes around the toroid once, it again reaches the starting point, right? So it has no place to exit the toroid. As in the case of a solenoid, you had two open ends from where the magnetic field used to come out, spread out from one end and go back to the other end. But in this case, the magnetic field is kind of trapped inside the loop here, and it only travels in this direction in a straight line, right, like that. And so it has no place to exit, and therefore there is no magnetic field outside the toroid in this space or in that space, because there is no place for the magnetic field lines to exit the toroid. And one more simple way in which we can find out why the magnetic field outside in this space or in that space the magnetic field is zero is by taking an Amperian loop. If I quickly take an Amperian loop somewhere here, I can very easily see that there is no current through the Amperian loop, and so there should be no magnetic field along the Amperian loop. It's as simple as that. And similarly, if I take a larger loop here, now you might be thinking there's some current through the loop. So this is your magnetic field, this is your toroid, and the surface of this the Amperian surface, which is enclosed by the Amperian loop, that goes right through the cross section of your toroid like this. And so the number of coils that are coming out of the surface in the upwards direction is equal to the number of turns going into the direction, right? Because how does the toroid go? It comes out, goes in, comes out, goes in, and it goes in this way, right, in the whole, through the whole surface. So the number of points at which it comes out of the surface is equal to the number of points it goes in. So it comes out at this point, goes in at this point, comes out at that point, goes in at this point, and so on and so forth. But both of them are equal, obviously, because it is made up of loops after all. And so again, the net current to the surface should be zero. And so again, because the net current is zero, there is no magnetic field along this loop outside the toroid. Now what we can do is we can again take a cross section of the toroid, and what we get is similar to the solenoid, and then we can take an Amperian loop through the toroid itself, and then let's find the magnetic field inside the toroid, right? So what I'll do is I'll quickly remove it. Now we know that so I'll just take the cross section of it. That should look like something like this. I'm just drawing the lower part of all the loops. Let's quickly draw that. I'm sorry for my bad drawing. I hope you are getting the point, but yeah, I hope it fits perfectly. So these are the lower section of the loops. So these are something like this, and there's the top section of the loop, and the loop continues. So because I have taken the cross section, I'm only left with the lower part of the loop, of all the loops. Sorry for my runny nose, but yeah. Now if I take a loop, an Amperian loop like this, through the toroid, what is the net current coming through this Amperian loop, or the Amperian surface enclosed by the loop? Now let's say this is the coil is going in that direction, so it comes up from here, goes in from there, up from there, into there. So it is coming up from here. I'll just put a dot there to show that it's coming up. So you have a dot all there, and I'll put a cross there because it is going in through that point. The current is going into the table from that point. I'll quickly put crosses everywhere, and yeah, so you have all these points at which the current goes into the table, and at all these points the current is going out of the table. But we're not concerned with all these points because they're outside our Amperian loop. They're not passing through the Amperian surface, but these crossed points are going through the Amperian surface enclosed by the Amperian loop, and so we're concerned by these points. And if I have to find the magnetic field along the Amperian loop, the black thing, how would I do that? Well, I can use my Ampere's law, which is again integral of B dot dl equals mu naught I. So even in this case, we know that the magnetic field would be parallel to the Amperian loop, so the magnetic field would be uniform inside the toroid, and so it will be constant along the length of the toroid. So I can take my B out of the integral. There I go. And also I know that the integration of dl would be simply the length of the Amperian loop. What is the length of the Amperian loop? So let's say this length is the radius. Let's call that r. So I would simply get b times 2 pi r, which is the perimeter of the circle, and that's the length of our Amperian loop, equals mu naught. What is the current going through the Amperian surface enclosed by the Amperian loop? Well, it will be simply I, which is the current in one loop. Let's say this, then it has I going in, yeah, and it's current I here. Now what is the total current going through the surface? It would be the number of coils or the number of wires that are going into the surface. Let's call that n, the total number of wires or total number of loops going into the surface, times the current Ni. So Ni is the total current going through the surface, and yeah, I'll simply take that there. Now I can simply solve for B. B equals mu naught Ni divided by 2 pi r. As simple as that. Now if I see here, n is the total number of loops, and 2 pi r is the length of the perimeter, or the length of the Amperian loop. Now before I proceed further, I'd like to just point out one thing. Generally the toroids we use are pretty large as compared to in their radius. So what happens is, as compared to their thickness, so what happens is this inner radius, or the distance from the center to this part of the toroid, the inner radius of the toroid is almost equal to the outer radius of the toroid. So this length and that length are almost equal. So what you can say is that this length and this length and this length are around the same length, so we'll just call all of them as r. Now what we get is, so what is 2 pi r? 2 pi r is the length of the toroid itself, right? So if we take the length of the toroid, or rather if we take the total number of coils in the toroid, divide that by the length of the toroid, we get the loops in the toroid per unit length. So n by 2 pi r is simply the total number of loops per unit length, which we generally represent by the letter lowercase n, and so this becomes B equals mu naught small n, which is the number of loops per unit length, times I. And if you observe, this is the expression for the magnetic field of a toroid, and if you remember, this is also the expression for the magnetic field of a solenoid. So by chance the expression for both the toroid and the solenoid is the same, and yeah, the only difference is that you have some magnetic field outside the solenoid because you have the ends through which the magnetic field goes out, spreads out and comes through the other end. But in case of a toroid, you do not have any such space for the magnetic field lines to exit, and therefore all the magnetic field is inside the toroid. And yeah, one small note here. Generally toroids are used to contain hot gases or things that are made of charges that are hard to store. So let's say you have some charges, and I give you some charges to store. What you can do is you can put those charges inside the toroid. Now you have magnetic field in that direction, right, which is parallel and it is contained inside the toroid itself. So if the charge is moving, it will move parallel to the magnetic field lines, and it will continue to move inside the toroid itself, and it cannot exit the toroid. So that is one way in which you can contain charges. And if one last point which applies to both toroids and solenoids is that you can use the right hand rule again to find the direction of the magnetic field. So what you have to do is you have to curl your fingers in the direction in which your the coils of the loop, the coils or the current in the loop is turning. So in this case it is coming out from here and going, sorry, it is going in through there, sorry, and coming out of there. So it is going in through here and coming out of there. So it's this direction. So this is, if I curl my fingers in that direction, this is the direction in which the current is curling around in the toroid. It's going in through here and coming out of there. So my thumb should point in the direction of the magnetic field. So in this particular toroid, I should have a magnetic field in that direction. So this is the direction of the magnetic field. So I have the magnetic field in that direction. And the same applies to a solenoid also. You can curl your finger in the direction in which the current in the solenoid is curling, and your thumb should point in the direction in which the magnetic field is present. So yeah, that is all there is to the toroids and solenoids. That's it for this video.